Okay, so let's get started. Just remember the homework is due, I believe, on Monday. Um, and then let me know if feel free to shoot me an email if you have any questions, and I'll answer them to the best of my ability. And again, if I get enough of them, I can arrange for some Zoom time on Saturday. If I do that, I'll make it available to everybody. But so far, I haven't gotten that many questions, so yeah, don't know if that's because you haven't started yet, or if that's because um, that that there haven't been too many questions yet. So, but anyways, so let's get started. So today we're going to talk about chemical kinetics. Again, this will be just a real brief review. If you want a lot more details on chemical kinetics, we need to take the normal combustion class. Here, I'm just going to give you a really broad overview. Typically, in that combustion class, by the time we finish chemical kinetics, we're about 6-7 weeks into the 6-7 weeks into the semester, if not more. So yeah, this is just a real brief overview. Okay, so first we just need to go over just what a reaction is, and first what an elementary reaction is. And an elementary reaction is a reaction where there's no intermediate species that can be detected or are necessary to describe its reaction process on a molecular scale. And so what is an intermediate species? So say if you consider the global reaction of CH4 plus 2O2 goes to CO2 plus 2H2O. You know, just based on how complicated the reactants and the products are, you know that there's a whole bunch of steps that is occurring in between the conversion of CH4 and O2 into CO2 and H2O. And so there's a whole bunch of intermediate steps that is needed. And there's a whole bunch of different gas species that basically come and go during that process. And those gas species that are neither present in the reactants or the products, but form during the reaction process, are called intermediate species. And these elementary reactions themselves do not have intermediate species. And they can be described with a single step based on one molecular collision. And what I mean by that is, at least for gas phase chemical kinetics, that basically, essentially, a chemical reaction for gas is just a giant game of billiards. And now all the billiard balls, our molecules, are colliding so hard that they can basically fragment and then reform. And so if you consider this reaction here, H2 plus O goes to OH plus O. OH is a common species that you will encounter. It's called hydroxyl. It is used a lot in experiments because you can actually use laser systems to excite hydroxyl and then make it fluoresce and give off light. And so with experiments, you can actually visualize where OH is and measure its concentration. So it's very useful. And so it's a very important species. And this reaction here can be explained in one molecular collision without any intermediate species. So here we have an H2 molecule just happily sitting here, and we have this O molecule that is just going to come in and sort of crash the party. And so this O molecule is going to come flying in, and it's going to strike this H. Molecule. Well, there's enough. Assuming this O atom is moving fast enough, there's going to be enough kinetic energy from that O atom striking this H atom, that it's going to shatter this bond. And this bond here, you can think of like a spring. So there's going to be enough kinetic energy here that it's basically going to break the spring that is holding these two H atoms together. And then as the two H atoms fly apart, the O and H atom are going to form their own bond, and you're going to have a lone H atom that's basically going to be flying off. And you could think of this lone H atom as a fragment of this high-speed collision. Or you can think of, or another way to think of is, to some extent, this O atom is like a bullet that is striking the H2 atom, or striking the H2 molecule. Okay, but this entire chemical process, you can easily draw up a configuration in your head where this OH can, where this O can become in contact with H to form one OH molecule, and another. Actually, this should be H. This reaction is not properly balanced. Minus 10 points, Orion. Um, so and so yeah, it should be H here, but yeah. So elementary reactions are 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 basically these. And now the law of mass action states that the reaction rate for an elementary reaction is directly proportional to the product of all the concentrations of the reactants. And that, and so given a general reaction like this, we have the sum, again, the sum of nu I double prime mi goes forward at some rate constant kf, and that goes to nu I double prime to moles of species I. And so the chemical reaction rate, and I'll have an example of applying these formulas in a couple of slides. The reaction rate for an elementary reaction is, I'll call this RR for the reaction rate. Sometimes you'll see that being Q being the reaction rate variable. Q is used for heat, so I don't like using Q. So I use RR. Okay, and so RR is just this forward rate constant, and we'll talk about that later on, times the product of all the concentrations in on the reactant side, raised to the nu I double, or raised to the nu I prime power. Okay, and so these two expressions here, they are actually the same. It's just two different nomenclatures for the concentration. And I actually like the square bracket notation best, but that sometimes gets really cumbersome to use. And so sometimes the sort of capital C underscore with the species name is more convenient to use for concentration. Okay, and again, this Kf is a forward rate constant, and we will discuss that later. And Mi in square brackets and Ci are both concentrations for species I. And the molar production rate using this, basically using this chemical reaction rate, the number of moles of species J that is being produced is just the difference in the stoichiometric coefficients between the product side and the reactant side, multiplied by the that's multiplied by the reaction rate. Okay, and so you can say the time rate change of the concentration of species J is just equal to the difference in the stoichiometric coefficients for species J times the forward rate constant times the product of all the concentrations raised to the nu I prime power on the reactant side of the chemical reaction. Okay, and then often when you're dealing with a physical code, you're more interested in the mass production rate, and that is the time rate change of species density, which is just the density, times the mass fraction of species J. Sometimes that's just listed as rho J. So rho times Yj and rho J are the same thing. And to compute them, you just take the concentration of species J and multiply it by the molecular weight of species J. Okay, so if you can find the time rate change of concentration or the time rate change of species mass by just multiplying them by a constant. Okay, are there any questions here? Okay.
Yj is mole fraction, right?
Which one?
Y sub j, that's the mole fraction?
No, that's the mass fraction.
That's mass fraction?
Yep, and mole fraction is X.
Okay. So what's the difference between mass fraction and concentration?
Mass fraction is just the fraction of mass, and concentration is the number of moles per unit volume.
Okay. So that would be mole fraction is concentrate. Is that different then?
Well, the mole fraction is the ratio of the moles of species I divided by the total number of moles in the mixture. And the concentration is the number of moles of species I divided by the volume.
Okay, volume versus number of total moles. Okay.
Yep. Any other questions? Okay. So now a global reaction is and you'll sometimes see these. They're sometimes called simplified reactions or global reactions. It's a reaction where basically many elementary reactions are simplified into one or more net reactions. And global reactions most of the time cannot be described by a single molecular collision. They normally cannot be described using a single step, and global reactions physically require many intermediate species to describe them. For example, say we had a global reaction of say methane plus 2O2 goes to CO2 plus 2H2O. So if you were to draw a picture of how this could occur in one step on the molecular scale, it would have to look something like this. You have you have the CH4 molecule just happily sitting here, and then it's going to be attacked by two oxygen molecules simultaneously. But these two oxygen molecules that have to simultaneously strike sort of halfway in between these, basically strike halfway in between these two, the halfway in between these two H molecules here and these two H molecules here, such that this O atom here interacts with the C, and this O atom here interacts with the C, and then the two free H atoms here then interact with this O molecule here, and the two free H atoms here interact with basically that O molecule there to produce H2O, a 1CO, and another H2O. So does that collision and that crazy correspondence in one step, in one molecular collision, does that seem very likely? No, that the chemical reaction simply does not happen like that. It is impossible. It requires first, it's impossible, but also it would hypothetically require perfect alignment in a simultaneous collision of these three molecules that have the right kinetic energy, the right orientation, and the right timing, and that just never happens. In reality, what happens is this O2 molecule will impact. If you think of this big CH4 molecule, what's it going to be? Basically, what is O2 going to be? What is O2 going to be more likely to strike? It's going to be more likely to strike one of these, basically one of these H atoms basically hanging off to the side. And so they're going to bump into the H atom, and they're basically going to rip it off, and you're going to wind up with say OH plus H, and you're going to wind up with a CH3 molecule, and then that CH3 molecule starts bumping into other things, and then more H atoms get ripped off. And so the real process here involves lots of collisions between all sorts of say different molecules. And often, because a global reaction basically represents a physical process that's really complicated, in the literature, you will often see them written like this, as some fuel plus oxidizer at some rate constant kg goes to some products. Okay, and so it'll be up to you to look at what they mean by ox. It could be O2, or it could be just based on air. And the products might be listed as, say, CO2, NH2 explicitly, and other times they will be just listed as products, and sort of that's it. And then you'll be given some properties of the products. And for these, again, there are all sorts of reaction rate models for the time rate change of the products. But the time rate change of the products will be equal to for like this reaction here would be equal to the global rate constant. And you'll very commonly see them raised to the concentration of the fuel, whatever that is, raised to the n power, and the oxidizer concentration raised to the m power, where this n and m are basically empirical constants. Okay, and they're normally not one, and like quite often you see 1.5 or even 0.5 or 0.3 sometimes for the basically for these constants. Okay, but now again, this entire process of the conversion of fuel and oxidizer to products, physically it is occurring on many steps. Okay, and so a chemical reaction like this just simply doesn't happen in basically one step. Okay. Now, before we go to our example, we'll just say that elementary reactions are usually reversible, which means they can react in the reverse direction. And we use this notation a bit when we were describing chemical equilibrium. And reversible reactions are donated quite often with a double arrow. And so you have nu I double prime mi goes forward at a rate constant kf, and it goes to nu I double prime moles of species I. And this reaction can also go backwards, and so it can also go from the product side back to the reactant side, and the rate constant for that is Kr. Okay, and so for these reactions, the chemical reaction rate for the forward direction is the same as it was before, using the law of mass action, and the reverse reaction rate can be found by, again, using the law, assuming this is an elementary reaction. You can use the law of mass action by simply flipping the reaction direction. So here I've taken this chemical reaction here, and I flipped it so that basically the nu I double prime is on this side and the nu I prime is on this side, which means that I flipped the direction. I've also flipped the direction of the arrows. So now Kr is pointing to the right because I've basically flipped the product and the reactant side. And then you can apply the law of mass action and find that the time rate change for the concentration for species J in the reversible direction would just be Kr times the difference in the stoichiometric coefficients. And so in this case, it's nu I prime minus nu I double prime times the product of all the concentrations. Actually, this should be I here. So in your notes, just basically mark that with an I, of the concentration of all the reactants raised to the nu I double prime power. Okay, and so it's just the law of mass action all over again, but instead of Kf, you have Kr, and you've interchanged nu I double prime interchange nu I double prime with nu I prime, and I'm gonna just factor out a -1 here and basically flip these. And so this equals negative. So the reaction rate, or the time rate change of molar concentration, is equal to minus Kr times the difference in the stoichiometric coefficients times this product term here. Okay, and so now if you want to combine these, because you can, believe it or not, the reaction can be can go both forward and backwards at the same time. That's actually how chemical equilibrium is achieved. Chemical equilibrium is not achieved by the chemical reaction stopping. Chemical reaction is achieved by the rate of production of species I in the forward direction being exactly equal and opposite to the rate of production of species J being destroyed in the reverse direction. Okay, so the net rate of production is 0. That does not mean that the chemical reaction rate itself is 0. Okay, it's just basically that they are equal and opposite. It's a bit like an equilibrium force. It does not mean that the force itself is 0. It just means you have an equal and opposite force pushing on your object that is causing it to not accelerate. Okay. Now, the net molar rate of production is just the sum of the forward rate of production and the reverse rate of production. And if I use the expression here for the reverse rate of production and add that to the one for the forward rate of production here, what I wind up with is this equals nu I or nu j double prime. This one here is correct. Nu j double prime minus nu j prime times the quantity of the forward rate constant times the product of the concentrations in the reactants raised to the nu I prime power minus the reverse rate constant times the product of all the concentrations on the product side of the reaction raised to the nu I double prime power. Okay, so just an example. We have this elementary reaction here. We have HO2, hydrogen peroxy, plus atomic oxygen goes to 2 hydroxyl molecules. So if you want to find the time rate change of hydroxyl, we can apply this formula here. Well, first, nu j double prime minus nu j prime. We have 2 here and 0 on the left side. So this number here is 2. And then, so we have a 2. So we are producing 2 moles of OH. We have the forward rate constant here, and we're going to do the product of all the concentrations of each reactant raised to the stoichiometric coefficient. So we have HO2, and there's only one of those, so that stoichiometric coefficient is 1. So we have the concentration of HO2 raised to the 1th power. Here we have hydrogen, or atomic hydrogen, I should say, and there's only one of those, so we are going to multiply that by the concentration of atomic hydrogen raised to the 1st power. And then in the reverse direction, we have two hydroxyl molecules. So the stoichiometric coefficient for that is 2. And so we're going to take the concentration of hydroxyl and then raise it to the 2nd power. So, and so again, we are just applying this formula here. So are there any questions with this so far? Okay. Now, what about this Kf? How do we find that? And for gas phase chemical reactions, it's often computed using an Arrhenius model. And recall that the reaction rate for an elementary reaction is given by some rate constant multiplied by the product of all the concentrations raised to the stoichiometric coefficients. And again, I am interchanging the square bracket notation and the C notation here, mainly just to get you used to that. You will commonly see both notations used in the lit, like say, Stephen Turns' combustion book uses square brackets, and Ken Kuo's uses the C's. So you just have to get used to seeing both. Okay, and the rate constant is usually modeled by an Arrhenius term, and this term in general is given by A, which is called a prefactor, times temperature raised to some nth power. That is an exponent. And we have this E, raised to the minus EA over RUT, and EA is the activation energy, and I'll discuss that in the next slide. And this term here is called the Arrhenius term. And if you remember, when I discussed how a chemical reaction proceeds, it proceeds by all these colliding molecules. Well, you could imagine if I go up to our first slide, you could imagine that if, say, this O2 or this O atom is barely moving, it's just going to barely hit the H2 molecule, and they're just going to sort of bump off of each other, and there's not going to be enough energy in that collision to actually rip off, to basically rip apart to basically rip apart this H2 molecule. So there is some amount of kinetic energy that is needed for the chemical reaction to proceed. So not all of these collisions are going to have enough kinetic energy to do that. And what the Arrhenius term represents is the fraction of all of those collisions that have enough kinetic energy to cause the reaction to proceed. Okay, so it's just the fraction of successful collisions that basically lead to a chemical reaction. Okay, and this expression here, sans this temperature term, you can actually derive it from the kinetic theory of gases. And in the other class, I do that. And in theory, basically, this represents the fraction of successful collisions. And basically, these two terms here are basically basically converting these two these two concentrations here, and if you multiply them by A and T raised to the 1/2 power, that is the total number of collisions. And so basically, this represents just the total number of collisions, and this term represents the fraction of those collisions that allow that have enough energy to allow the chemical reaction to proceed. So now for the activation energy, because I talked about that and that's important here, is the activation energy is the amount of energy needed for the colliding molecules to react again at the molecular level. So you could imagine we have some reaction coordinate here on the x-axis here, and so here we have a pair of molecules in the reactant state, and we have the molecules on this side on the reactant state. And if we plot the energy as a function of the sort of reaction coordinate, just think of it as some dimensionless thing, the amount of energy in the system, or the amount of energy, is going to go up, then it's going to go down. And so basically, to get the reaction to proceed, there has to be enough energy in the collision to raise the total energy of the molecules above this threshold here. Okay, and basically this difference between the peak energy, or the peak chemical energy, and the energy of the reactants is called the activation energy. And then you can think of this like a hill. If there's enough energy to get it to the peak, then it can just slide on down to the product side. Okay, and there is also for the reverse reaction, you can also think of an activation energy for the reverse direction, and that's given by basically just this distance here, and this distance here is actually just the heat of reaction. Okay, and so this is just an energy diagram, and it includes the activation energy and the heat of reaction, and also that's why there's that's another reason. Not only does the Gibbs free energy not favor the spontaneous conversion of, say, CO2 into methane, or say gasoline, not only does the Gibbs free energy say that, the Gibbs free energy and the second law say that's not going to happen. Also, there is a huge amount of there is a very large activation energy that is required. And so products just don't spontaneously convert to reactants from an energy standpoint. Too, is that there's just a huge energy barrier that is needed for that chemical reaction for pure products to go into the reverse direction en masse. You may have one or two, a small subset of them going backwards, but not very many. Okay, and so that's just a brief idea of what the activation energy is. And also in the literature, you'll sometimes commonly see the activation temperature, and that's just the activation energy divided by the universal gas constant. And you'll sometimes see this being basically being given. You'll sometimes see instead of activation energies, activation temperatures. And now one thing that you need to consider is that you will look at these and you'll see activation temperatures of say 15,000 Kelvin, 20,000 Kelvin, 30,000 Kelvin. And you may be thinking, wait a minute. So if I convert the energy of the collision into temperature, I'm getting 30,000 Kelvin, but my flame is at 2,000 Kelvin and it's definitely reacting. How in the hell is that flame reacting? Okay. And so why it's reacting is that you need to think all these reactions are occurring at the molecular level. And so at the molecular level, temperature is the measure of the average kinetic energy of the molecules. So if you take all 10 to the 23rd molecules and you basically query their kinetic energy, that is how fast they're moving, how fast they're rotating, and the amount, and basically how they're vibrating. You take them all and you add them up, and average them, you get temperature, or a measure of temperature. Okay, but you're going to think about there's going to be a very wide distribution of the kinetic energy of each molecule on an individual basis. You'll have some that are just as the molecules are just randomly jiggling about. You'll have some that are almost stationary, and you'll have some that are acting like baseballs and just sort of flying through, and so and are moving very fast. And so there's a very small percentage of those molecules where if you were to measure the temperature, or if you were to convert the kinetic energy into temperature for that one molecule, I mean, that doesn't make sense. But if you were to do that, you would get say 50,000 Kelvin for just that one molecule. And so there's a very small number of those molecules, but yet it's those molecules that have it's those small number of molecules that have this kinetic energy that is greater than the activation energy, which then cause the chemical reaction to proceed. Okay, and so that's sort of and so all of this gas phase combustion stuff, you can really think about it physically at the molecular level as a bunch of molecules colliding with one another. Okay. Now we discussed activation energy in the forward rate constant. How do we determine the reverse rate constant? Well, we apply the chemical equilibrium condition that the time rate change of moles is equal to 0. And if the time rate change of the number of moles of species I is equal to 0, that also means that if you just divide this by volume, you get the concentration. That means that the time rate change of concentration is also equal to 0 for all species. So recall that our expression for the time rate change of concentration is here. And it's going to be equal to 0. So that means this term here, that does not matter. And so you basically have this term here in the square brackets being equal to 0. And you can solve for Kf over Kr. Okay, and you get this expression here. And this is defined to be a Kc of T, which is an equilibrium constant based on temperature. Okay, and so if you, and then I'm not going to go through it here, but you can actually substitute in for concentrations. You can actually use the ideal gas law and get this in terms of partial pressures and mole fractions. And you can actually relate Kc to the Kp that we had, or the pressure-based equilibrium constant that we had in the equilibrium slides. Anyways, I'm going to skip the derivation. It's in just about every single combustion book there is. But if you substitute in the ideal gas law and convert concentration to partial pressure, and the mole fractions, you will get that Kr is equal to Kf uh, over P naught over RUT raised to the delta nu, where again, delta nu is just the net change of moles from the product side to the reactant side of the chemical reaction times Kp of T. And again, Kp of T is equal to minus delta G naught over RUT. Okay. And so basically you can use, typically you are given Kf, but the Krs in a reaction model are not listed. And so if you want to, if you need Kr, you need to use this, condition here to compute Kr. And for an ideal gas, it just turns out being basically being this. Okay. Now, so we discussed ideal gases. Now we need to discuss how to deal with this for real gases. This is a point that when I review papers and things like this, you see a lot of folks getting into this, like if they're modeling rockets and things like that, that use real gas equation of state, such as liquid, such as rockets using liquid oxygen. Those often use Peng-Robinson equation of state. Is that I'm not going to go through the derivation, but essentially you can apply the law of mass action right here, but instead of the concentration of species I, you use what is called the activity concentration, AI. And this is a real gas corrected thermodynamically concentration using and this it's just sort of corrected. It's a concentration that is corrected to account for the real gas effects in the chemical reaction process. And you can show, which will be part of a homework problem, that this activity concentration is just the fugacity coefficient times the compressibility factor times the normal concentration or the normal molar concentration of species I. And so basically, if you have a chemical reaction model for that is written for an ideal gas and you want to correct it to include real gas effects, all you do is wherever you see a concentration, you replace that concentration with the so-called activity concentration. And then you'll be guaranteed, if you do that, to get the correct chemical equilibrium. Okay, and it turns out that if you use the activity concentrations, if you know Kf, which is still the same Arrhenius model, Kf over Kr is actually the exact same thing. There is no difference. Okay, and so that's one of the nice things about doing it this way. And also, again, these activity concentrations are used a lot by chemical engineers and chemists dealing with liquid solutions and things like that. Okay, so are there any questions with this so far? Okay, and again, this activity concentration thing is a mistake that I see quite a bit when I review papers in this area. It's something that that mechanical and aerospace engineers normally just don't know about. And so they make a big deal about using, say, Peng-Robinson or something like that in modeling rockets, but then they forget to correct for the activity concentrations, and then most of them simply just don't know that it's there. And it's not their fault, is that this is really getting into chemical engineering thermodynamics. But yeah, and so that's just something to be aware of. Is that for real gases, you need to include the activity concentration. And in fact, for the code, for the Cantera code, I looked through their source code and they actually base all of their reactions off of the activity concentration. So for their ideal gas model, they also compute an activity concentration, but for an ideal gas, phi I and Z are both 1. Okay, but they still do those functions anyways for the sake of being general. Okay, now we've just discussed one reaction. But now you can have many simultaneous reactions occurring at the exact same time. So a reaction mechanism is a series of elementary reactions by which an overall reaction proceeds. And these describe the overall process behind a global reaction. So if we are to consider a global reaction as 2Al goes to 3 halves O2, goes to Al2O3, and you can immediately tell by looking at this that this is a global reaction. Because how do you have 1.5 moles of O2? That makes no sense. Oh, okay. And if you were to say double this to have 4 aluminums and three O2s, well, to get that reaction to proceed, that would you would need the simultaneous collision between 7 different molecules in the perfect orientation, and that just doesn't happen. Okay, so you can immediately tell by looking at this that this is a global reaction. But there are lots of models for this. And basically you have this whole series of chemical reactions here, and alongside each chemical reaction, we have the prefactor A, the temperature exponent, and the activation energy. So this is traditionally how a series of chemical reactions are basically listed, and all of these chemical reactions can occur simultaneously. Okay.
Professor, can I ask a question?
Yeah.
When we mention activation energy, are we specifically talking about the E, I guess, constant in there, or is it the E to the minus E over RT? What do we refer to as activation energy?
It would be the EA.
Is that the exponent to the? It's just the E sub A. Okay.
Yeah.
Not that whole term E to the minus E sub A over RT.
No, well, because they can't give you that term because
it's a function of temperature.
It's a very strong function of temperature.
Okay.
Extremely strong temperature. For low temperature chemistry, a rule of thumb is for every 10 degree Kelvin rise in temperature, you double the reaction rate. So this is an extremely strong function of temperature, and essentially this function here, it acts like a switch that turns the chemical reaction off at low temperature and makes it react rapidly at high temperature. I mean, you should plot it once. It's a very strong function of temperature.
And then one other kind of thing to go off of that, you mentioned that like a flame being a much lower temperature than, say, the activation temperature, because the activation temperature is just, what maybe a few molecules are at to get the reaction going. So can you think of, as you progress in stronger reactions from a burn to a deflagration to an explosion and so on, can you think of that as a larger number percentage of molecules at that activation temperature at one time? So that would kind of be the correlation. The higher percentage at a given time, the more devastating or powerful your reaction is going to be. And that's kind of how you run to detonation.
And a deflagration, yes. And so that's basically what happens is you have a few molecules that sort of slowly get it going, and those release energy. That increases the average temperature, but locally near the reaction zone, basically you can think of all these fragments, they just go flying off everywhere. Those fragments are moving at high speeds, they crash into the neighboring molecules, and it sort of keeps cascading like that. Okay. And so basically, yes. That's why a chemical reaction, it's sort of slow to start, but after it gets going, it actually really takes off really rapidly for that reason. Okay. And now detailed mechanisms can also be called semi-global. And if they are semi-global, that means they are a series of elementary reactions, which are right here. And they may have a global reaction in them to describe some process. Okay, this is just one that I used in my PhD thesis. Yeah, and just be aware that of the different nomenclatures. Also, you'll sometimes see the same species basically listed by different names. So here, this is species ALO. ALO is AL20, and I listed it back in the day as AL20, and so they are the same thing. So just be aware that there are different names for different species in these reaction mechanisms. Okay, and then also just be aware that even though there are some sub processes in a chemical reaction mechanism that may be described by a global reaction or two. Sometimes, like we are also adding carbon, or a student of mine is adding carbon reactions. Those carbon reactions are two global reactions to our aluminum oxidation mechanism. Okay, and for a reaction mechanism, the net molar or mass rate of production for a is the sum of the rate of production for basically all of the chemical reactions. So if you want to find the total time rate change of concentration of species K, uh, we we basically have to sum the rates of production of that species over over every single reaction. Okay, and so that's basically what this is doing here. And so I'll just basically show this by way of example. Say we have this reaction here and this reaction here, and we want to find the time rate change of O2. Well, the net change of stoichiometric coefficient for reaction 1 is -1. Then we apply the law of mass action in the forward and reverse directions. So we have Kf1 times the concentration of H2 times the concentration of O2 minus Kr1 times the concentration of hydrogen peroxide times the concentration of H. Now we add to that the rate of production for the second reaction. And so the net change of moles across the second reaction for O2 is again -1. So I'm going to I'm going to multiply this by -1. Then I have Kf2 times the concentration of H times the concentration of O2 minus Kr2 times the concentration of hydroxyl times the concentration of H. So again, you apply the same thing, just about a bit, but basically just once for basically each reaction. Okay, and so that's that. Uh, and there are some special reactions. I thought I had something on third bodies. I'm missing a slide. So I will skip that for the time being and get to that on Monday. But one thing I will say is, how are the Arrhenius parameters determined? They're often done in shock tube experiments, where I'm not going to go over the basic shock tube physics, but one thing that a shock tube does is it sends a shock wave down a tube, and that shock bounces off the end wall. And for a few milliseconds, you have a very controllable a very controllable region behind that reflected shock, where you can control the pressure and temperature and chemical composition. So you can fill the shock tube with some gas, and you send the shock wave through it, and you have a very controllable high pressure, high temperature, and you can just basically you can measure the concentration of some species as a function of time, and then you can basically fit the chemical reaction parameters to it. So, but that depends on your assumed reaction model and things like that. So let's just say we are filling this section here with a bunch of A2 molecules, and we are proposing the breakdown of A2 into 2A molecules. And our chemical reaction model basically looks like this. This would be called a first order reaction, and the reaction order commonly given by N. There are lots of N's in chemical kinetics, but they're used in all in different contexts. So they shouldn't be so there shouldn't be too much a confusion of which N is which. It's not like V in fluid mechanics where it's used in everything. Where the reaction order is the sum of the exponents in the concentrations. So if I was to write the expression for the concentration for this, you'd have dA2 is equal to minus Kf times the concentration of A2, and the sum of the concentrations in this rate of production is 1. So the overall reaction order is also 1. And so I will finish this stuff on chemical kinetics on Monday. So I'll stop recording here real quick.